Welcome everybody to the special workshop on EXtremePV that we are organizing for the first time under the umbrella of Pvcon 2020. And this is again Hisham Nasser from Gunam, Metto. And I have the honor to chair this exciting workshop on EXtremePV. Now we will start with the first keynote speaker, Mr. Said Ahzi. So I will give a short introduction about the speaker. So he has his academic career includes several research, teaching, and administrative position in the USA, France, and Qatar. And currently, he's a visiting professor at Texas A&M in Qatar, and he's only from University of Strasbourg in France, where he holds a distinguished professor position. Previously, he had the position of principal scientist and professor at Qatar Environmental and Energy Research Institute, QERI, and Hamad bin Khalifa University in Qatar. He served as acting research director of the Material Engineering Group, as well as Computational Material and Process Center at QERI. He also holds an adjunct professor position with the School of Material Science and Engineering at Georgia Institute of Technology in the USA, and he had advised more than 30 PhD and 25 master students, and he published more than scientific paper in the area of mechanics, materials, material processes, and manufacturing, biomechanics, and thermomechanics. So, Said, do you hear me? You have your presentation recorded, or you will go online?
Hello, everybody.
Okay.
My name is Said Ahzi, and I will be presenting my work on multi-physics approach for the computational analysis and prediction of performance and fatigue failure of PV panels. This work has been conducted in collaboration with Shahzada Pamir Ali and Nicola Bart from Qatar Environmental Energy Research Institute at Qatar Foundation. But I'm currently, I left QERI, and I'm currently a visiting professor at Texas A&M in Qatar, but I'm also only from the University of Strasbourg. So I would like first to thank the organizer for inviting me to give this presentation. So, as you all know, solar energy has certainly a lot of advantages such as abundance, almost evenly distributed worldwide, less maintenance, and so on. However, it also has some disadvantages, such as the fact that we cannot harness energy during night time. Also, another problem is it may require large areas actually for installing a PV, for instance. Now, PV system performance. In fact, the overall performance of a PV system relies on four metrics. These metrics are the performance of the radiation and optical part, then the thermal performance, and then the electrical performance, and the structural performance. So the radiation optical performance is measured by incident and absorbed radiation. Thermal is measured through the PV cell temperature, and the electrical performance is through the maximum power and efficiency, electrical efficiency. And the structural performance is a measure of the lifespan. How long would the PV panel last, actually? And currently for polysilicon PV panels, which I will be considering in this study, the lifespan that is given by the manufacturer is about 25 years. But this is completely dependent on the weather conditions where the PV panel is installed. Now, multi-physics modeling and that we are developing, so is based on the four sub-models. One is the radiation plus optical modeling, and second is thermal modeling, and third is electrical modeling, and finally the structural modeling. As you can see on this picture here, or this schematic, so the radiation is connected to electrical modeling, but also to thermal, and then thermal is connected to electrical and structural. So this is a fully coupled, where each model involves different physics, and that's why we call it multi-physics approach. Now, the motivation is to develop an accurate simulation tool for better visualization and assessment, to mitigate prediction errors at each submodel, and to reduce computational time, but also to improve reliability and credibility of the predictions. Now, I'll start with the first submodel, which is radiation and optical modeling, where there are several models that exist in literature, but we propose a simple one, and that is to compute the incident PV cell irradiance through this relationship here, where GPOA is the global irradiance of at the plane of array, and alpha is the effective absorption of the PV cell, and theta is the average transmittance of the glass, which is given by the relationship here, which involves the glass extension coefficient, the glass thickness, and also the incident angle, as well as the transmission angle. Now, for the thermal modeling, we use the classical heat equation, which is given by this relationship, where rho is the density, C is the specific heat, small t is the time, and capital T is the temperature. And then K is thermal conductivity, and Q is the internal heat generation. This schematic here on the right shows the elements of the PV that we are considering in our simulations. The glass, okay, since we are dealing with monofacial, so we have the top part is the glass, the bottom part is the Tidler or back sheet, and then the middle is the PV cells that are encapsulated using EVA, which is a polymer material. Now, we are neglecting in this first approximation, we are neglecting the anti-reflective coating, which is very thin and it will not change much the results. We are also neglecting first the copper interconnect ribbons, which are also very thin, but just to calculate the temperature, it's not going to change much the results. However, later on for structural modeling, because we are going to look at the fatigue of these ribbons, we are going to include them. Just to give you an idea of some of the work that exists in literature, there are a lot of modeling works, but they have certainly their limitations and their advantages. But what we're listing here is some of the disadvantages of these models. Either they are not fully transient, or they require too many parameters, or they overestimate the results, and so on. So in fact, our motivation was to come up with a simpler modeling that is fully coupled and that is transient, that will allow us to predict transient temperatures. Now, in our development, we first started with one-dimensional finite difference model to calculate the temperature, the distribution through the thickness of the panel. Then we extended that to a two-dimensional finite difference model by implementing our modeling into a MATLAB. And we also used finite elements, 2D finite elements and three-dimensional finite element, by using the commercial software ANSYS. Now, first, for the thermal modeling, the loads and boundary conditions. In this, we calculate the internal heat for PV cells by using this relationship here. This is the internal heat generation. S is the incident PV cell irradiance. The A is the area of the cells, and V is the volume of the cells, and eta is the important factor here, is the efficiency, which is taken to vary with temperature. It will decrease with temperature according to this linear relationship for polysilicon based PV panels, and the internal heat generated at the front glass is also given by this relationship here, where GPOA is the global irradiance at the plane of array, and the area of the A is the area of the panel, and V is the volume of the panel of the front glass. Front glass, actually, not the panel, the front glass. Alpha is the absorption coefficient of the front glass. And also for heat transfer, we considered conduction, convection, forced as well as free, and radiation, sky and ground, as shown in this schematic here. Now, first modification we made is to look at the look at the heat dissipation in the literature, and most of the existing models, or I would say all of them, use this type of schematics here. In fact, this is just to look at the boundary conditions on the top and bottom and the sides of the panel. But in fact, when you look at this, we decided that these boundary conditions are not correctly set, particularly the sink temperatures. What we did, we modified. As you can see here, the top sink temperatures are defined differently from the existing model. The bottom as well as the sides. So included the effect of the sides as well. By doing so, we were able to increase the accuracy of the prediction of the temperature distribution or temperature in the PV panel. Here is one first simulation where we use the input from the outdoor testing facility at Kiri, Qatar Foundation. This is the input for the ambient temperature for incident POA for 1 day. Full day on May 2013, and this is again the input from the wind speed during the same day. So this is input that are put into our model, two-dimensional model. As you can see, if we use the if we use the classical model for heat dissipation, well, we get some results that are fairly close to the experiments. The experiments are given here in red or orange, and the model is in blue, but with the root mean square of about 3. So not too close, but close enough. So now when we introduce our modifications of the heat dissipation, well, you can see the predictions are very, very close to the experiments with a root mean square of 0.8 only. So this is a very important improvement of the prediction of the temperature distribution or temperature in the PV panel. However, just to give you some precision here, the temperature that we measured here is the backsheet. So we are taking the simulated at the backsheet, not the cell in this case. Now, to make sure that the prediction work well for different days, we took a sunny day with clear sky, we took a sunny day with cloudy sky, a rainy day with overcast sky, and then 2 sunny days, consecutive sunny days. As you can see in all of them, our prediction of the temperature at the back sheet is very, very close to the experimental one, to the experimentally measured one. So in fact, we are now confident that our temperature prediction is extremely well compared to experiments. Now, we would like also to show you the results from one-dimensional. So we did the same thing one-dimensional, because the previous one I showed was for two-dimensional finite difference. For one-dimensional, as you can see, we introduced again the same boundary conditions at top, bottom, and side, and we were able to also improve the results for one dimension. As you can see here, for this day, sunny day on June 24th, this is a sunny day, cloudy sky on January 2014, and this is a rainy day on March 2014. Okay, these are the inputs actually for ambient temperature and incident POA, plane of array. Our simulated temperature at the back sheet compared to experiments for the 3 days is really good. So which means that we probably just for temperature prediction through the thickness of the panel, either at the back sheet or at the cell, we don't need maybe 2D, just 1D is enough. However, 2D is needed if you want to look at the distribution, not just through thickness, but also in the plane of the panel. Now, we also performed finite element simulations, as you can see here, 2-dimensional finite element to 3-dimensional finite element by using a CAD model for the PV panel, and looking into nominal operating cell temperature, and also looking into a 1 day in Doha, and looking into the temperature in the back sheet. As you can see, the NOCT compared to what is given to in the data sheet of the PV panel compares really well. And also, I thought this is the steady state, but for transient, as you can see, we have for 2D and root mean square of 0.3. For 3D, the accuracy is better, which gives a root mean square of 0.6. But again, 3D is heavily, it requires heavy computations, a lot of time. So as with an RMSE of 0.3, 0.8 is enough, in fact, unless we are looking for, again, some details for the, as you can see later on, for the structural analysis, we certainly need to go to 3-dimensional. But we will see how we can reduce the computational time in the structural modeling. Now, for the electrical modeling, electrical modeling is done to estimate the maximum power. Okay, as you can see, again, the model is this is we talked about radiation, we talked radiation modeling, we talked about thermal modeling, now the electrical. All right, so either we can get the Pmax from the full modeling of the IV curves, okay, or there are also some simple relationships given in literature if one wants just to estimate the maximum power. So as you can see from this paper here, that summarizes existing relationships to estimate the power, there are many models. So which one to trust, it all depends on the application. In our case, we decided to go ahead and use full model for electrical model by using and simulate the IV curve by using 1-diode model. As you can see, the 1-diode model is given by this relationship here, which involves 5 parameters. And this is the drawback of this type of modeling. So how to estimate these five parameters, which has the photon current, diode dark saturation current I0, series resistance, shunt resistance, ideality factor. Okay, so usually we use iterative methods or optimization techniques to estimate these. But the other thing is these 5 parameters depend on both the irradiance and the cell temperature. So how to include and account correctly for the effect of the irradiance and cell temperature. If we look at the literature, the Soto and co-workers proposed what we call a translation equations for the photocurrent, okay, which depends on the irradiance and the cell temperature. The I0 depends only on temperature. The series resistance is constant. The shunt resistance depends on the irradiance, and the ideality factor on temperature. So, but as you can see, most of them depend only on temperature on G. One of them is constant, and only the photocurrent depends on both temperature and irradiance. In our case, we would like to include the effect of both, and we came up with a new approach to calculate the shifting of these parameters as function, 5 parameters function of both irradiance and temperature. So if we take one of these 5 parameters, call it P, and then the variables are either irradiance or cell temperature. Okay, then we took the IV curves from data sheet for different irradiances and for different temperatures, and we try to fit the results, the IV curves, and see how each of these properties, 5 properties, evolve, either with irradiance or with temperature. And from this, we were able to come up with a unified relationship that gives any of these 5 parameters as a function of both irradiance and temperature in this form here. So this is the first time that this novel shift factor based approach has been used in the one diode model to predict the effect of temperature and irradiance on the 5 parameters of the one diode model. Now, if we compare our results to those of the SOTO estimates, as you can see, the photocurrent is the same here if we keep temperature constant and vary Z, but the other parameters are completely different. As you can see here, the series resistance is constant by the SOTO. In our case, it varies drastically. The same thing if we keep the irradiance constant at 1000 watt per square meter. The series resistance is constant by the SOTO, but in our case it evolves a lot. Okay, so as you can see, for both cases, a fixed temperature or fixed irradiance, our model predicts completely different results from the SOTO, except for the photocurrent, which are very close actually. Now, the other thing is if we compare our results or predicted results to IV curves, as you can see here, for a wide range of irradiance from 200 to 1000 watt per square meters, our model predicts very well for all of them, but the SOTO predicts only the case for 1800, okay, and not the other cases. So our approach is much better in terms of accuracy of the prediction. Now I move to the last part, which is the structural modeling, where we involve continuum mechanics actually to analyze the fatigue behavior of PV panels and failure. So if we look at the different loads that the panel is subject to, it could include wind, hail, snow, weight, and so on, but also this is the mechanical load. If you look at also thermal load, well, thermal load is due to temperature variations during each day, and then we may include also radiation, which leads to degradation of UV. UV degradation of the EVA, which is the polymeric material. One may include also chemical loads such as moisture, which increases the corrosion. However, if we look at the main source of failure of PV panels, in fact, corrosion is 45%, and the breakage of the copper interconnect into 45. We are interested in this case. We are not considering corrosion. We are considering only the breakage of the copper interconnect. As you see here in this picture, you see we took this geometry, which is in fact an old design, and we looked at how these ribbons may fail under thermal loading only. We did not consider any wind or snow or so, just thermal or radiation or chemical loads. We considered only thermal loading. And thermal loading, of course, because of the mismatch in the coefficient of thermal expansion between the different layers constituting the panel, obviously you're going to develop thermal stresses, and they are cyclic, because you heat and you cool, you heat and cool. So these are cyclic loads, and these cyclic loads will lead to fatigue failure. So now and in this case we are including the ribbons, actually the copper ribbons, as you can see, as an additional element compared to the first simulations where we looked at only the temperature distribution. Here we're looking into mechanics, and in particular the mechanical behavior of the and fatigue behavior of the copper ribbons. Now, to perform simulations of this fatigue behavior, one can run a three-dimensional analysis, which is computationally heavy. Well, we did not go this way. What we did, we took only one string of the panel, not all strings, and we performed a two-dimensional analysis. Okay, and once we once we found the area of maximum stresses or maximum deflection or deformation, then we focused on that area and we use a three-dimensional finite element method. As you can see in this slide here, so our proposed modeling is called a two-dimensional global and three-dimensional local. So based on one string, two-dimensional simulations, we define the maximum deflection, which leads to maximum stresses, and it happens to be in the central part of the copper ribbon, as you can see it in this case here, which is not surprising. Now we take whatever boundary conditions in terms of temperature and stresses and so on apply to this, and we use a finite element, three-dimensional finite element, as you can see it from this 3D mesh, to analyze the fatigue behavior of the interconnect. Now, to do so, we need to assign mechanical properties or constitutive laws for the different layers forming, actually, or different elements forming the PV panel. Silicon is taken as linear elastic with the coefficient of thermal expansion varying with temperature. The copper also has CTEs varying with temperature. The glass is linear elastic. Of course, silicon is also linear elastic. And the copper is in fact elastic plastic, so it has linear elasticity. Then we get to the yield point, and then we have plasticity. So we considered linear elasticity with plasticity, with the hardening, and this is kinematic hardening. For the EVA, which is a polymeric material, this is a viscoelastic material which is also highly dependent on temperature. We took a viscoelastic model which is temperature dependent, and that's what we input into our finite element simulations. Now, to include the initial conditions coming from the processing or the making of the PV panel, we looked at the lamination process. And lamination process consists globally of heating and then cooling. But when you cool, of course, the copper has suffered deformation, because you can see the residual stresses here, or the thermal stresses from the cooling after lamination, is about 158 megapascal, which is much higher than the yield point. The yield point is about 94 megapascal for the copper. So which means that during the lamination process, the copper interconnect has suffered plastic deformation. So we have to account for these initial or residual stresses in our calculations. Now, to analyze fatigue, of course, our panel is subject to, or the ribbon, because we are looking into the ribbon in detail, in more details, is subject to a cyclic temperature over time. So how to simulate this cyclic temperature variation, heating and cooling? We just take one day, okay, and then we repeat it many times, okay, in terms of the variation of temperature in that day. And we calculate, from this, we calculate the stresses and also the strains, and particularly the plastic strains, and particularly the amplitude of the plastic strains. So everything is cyclic, okay, and in particular plastic strains are cyclic, and we are interested in amplitude. Why are we interested in amplitude? Is because we are using a fatigue model to predict failure called Coffin-Manson model, which gives the number of cycles to failure as a function of the amplitude of plastic deformation that the ribbon or copper ribbon suffers. This model involves actually two parameters, which are fatigue ductility and fatigue ductility exponent, and these are taken from the literature measured relationship. So N is the fatigue life cycle, and this is what we are looking for, and we can, this is in fact will give us a number of days that will that the panel will be functional before it fails. Now we take the 1 day in January and 1 day in June from Doha, from our outdoor testing facility, and we simulate the stresses during that day. As you said, this is the temperature actually in the panel or in the PV cell, and this is temperature for the January in the PV cell. Okay, and we looked at the same day, okay, and see how the stresses evolve. As you can see, you have some relaxations due to the fact that temperatures increase. Okay, but from this we repeat this same day, we repeat it 25 times, okay, and then we calculate the so this is a cyclic loading that we have, and we calculate the plastic strain. As you can see, the amplitude of plastic strain stabilizes. It is a little bit higher in the beginning and stabilizes at 20 cycles or 20 days. The same thing for the case of January. Okay, it stabilizes after 20 days or even a little bit before, and we use our model to predict, in fact, the number of cycles. In fact, via Olicon stabilization is, in fact, to use this model here, we need to make sure that delta epsilon plastic stabilizes, okay, before we can use it. So it stabilizes at 20 cycles, and now we use this stabilized delta epsilon plastic, and we calculate the number of cycles or number of days that the panel will survive before it fails, or before the ribbon, copper ribbon fails. Here we have the number of days for January, and number of days for June, and if you convert this into years, you can see that here in Doha, if we repeat in January, if the weather was always like the day we chose in January, it will survive 21.7 years. But if we use the other extreme, which is June, we have only 11.2 years. So if we take the average, it's only 16.5 years, and if you compare this to what the manufacturers give, which is 25, is much less. As you can see that the weather conditions, such as the desert conditions in Doha, with high temperatures, will affect drastically the lifetime of the panels, and we cannot count on the 25 years that is given by the manufacturers. So we have to make sure to redesign our panels if we want them to last longer, to redesign them to be able to survive the harsh weather conditions in the desert areas. So with this, I will conclude that we have developed a radiation plus optical model using a simple and efficient approach. A thermal model based on one-dimensional, two-dimensional, and also three-dimensional finite finite element, but 1D and 2D as finite difference. We have also developed in the electrical model, we have developed one diode model. We have developed a novel concept for the based on shift factors to capture the variation of each of the PV parameters R5 as a function of radiance and temperature. In structural modeling, we developed a 2D global and 3D local to predict the lifespan of the panels. And overall, we have developed a unified simple approaches, and with increasing accuracy at each model. And then we also developed approaches to reduce drastically the computational time. And with this, I'll thank you, and I'm ready for any questions. Thank you.
So thank you, Said, for this rich talk and nice results you shared with us based on real PV module operating conditions. Now it's time to have one or two short questions because we are a bit late. From audience, if there are any question, if there is any question. So one of the question is, so from audience is that hot weather is always there, and so how to get the maximum power point from solar module in hot climate, or what are the strategies to eliminate the drawbacks that you discussed? I mean, that hot climate put on PV modules. So did you get my question?
Yeah. Do you hear me?
Yes.
Okay. So we did not look at any particular strategy here. We wanted first to understand the failure and so on. Now, if you look at just from failure point of view, we have to redesign maybe the copper ribbons, different geometry, maybe different dimensions, and so on. But we can also come up with ways for reducing temperatures such as cooling, but the cooling will be, unfortunately, is out of question. A lot of people have looked at this. Cooling is going to be very expensive, and there is no efficient way of doing it. Um, uh, so I think it's just redesigning by selecting better materials, better geometries, and that's one of the strategies. But again, and one thing we have neglected, I did not mention it in my presentation, we did not look at the dust or soiling effect. And that's also something that needs to be added. And we have some experimental results from the OTF, and we are going to make use of those, where we came up with strategies. In fact, based on those experiments, we came up with strategies to clean. What is the best and efficient way in terms of time, in terms of cost, to clean, either every week or every month or so. I will not go into this detail. There are some colleagues working on that. But from those results, we also have an idea of how to modify our optical model in order to account for soiling effect, and how that would maybe modify a little bit our results. So I think one of the colleagues from Fraunhofer is
Yeah,
going to talk about strategies, and hopefully we'll go to that. And actually,
yeah,
we have met before. They have been here at Doha, so they may have better
yeah,
answer. We did not
yeah,
look at the strategies for now. We looked at to understanding first what needs to be done, where the failure comes from, and
yeah. Thank you. So thank you again, and hope to see you soon in better conditions. So,
inshallah.
okay. So now I move to the next exciting keynote on investigating challenges and solution for desert PV application will be given by Dr. Clemens Ilse, who has about 10 years experience in working as scientist in solar at Fraunhofer CSP in the areas of microstructure, electrical, optical characterization of solar cell and module components, testing device development, standardization, and data analysis. So his research is devoted to solar energy application in desert environment. And now in Fraunhofer CSP, he works as team leader and currently leads numerous research and industry projects with focus on soiling and cleaning on PV modules. And I suppose that Clemens has pre-recorded the presentation, so we can listen to it now.
Hello everyone, I would like to welcome you to my presentation on the topic investigating challenges and solutions for desert PV application. My name is Clemens Ilse and I work at the Fraunhofer Center for Silicon Photovoltaics CSP in Halle in Germany. I'm happy that we have the possibility to present our research results here at the Pvcon 2020. In my presentation, I will start with a short motivation on desert PV, then I will give an overview of environmental stress factors and dig then a little bit into our results on solutions for performance and durability, considering high temperature stresses, temperature differences, UV degradation, and also a strong focus on soiling. I will conclude with some summary and conclusions. So why are we talking about deserts? If you look at this map, you will find that about 33% of the land surface is covered by deserts, which is a huge amount of our global land space, which is currently often not used. So there's a lot of potential for installing PV in these places. On the other hand, here you can see the photovoltaic power potential, with a color scale indicating the annual obtainable kilowatt hours per installed kilowatt peak for different regions of the world. As you can see, the PV power potential is especially high in the desert environments like the Sahara.
An area as big as a black square would be enough to serve the electricity demand of the world. In comparison, in Germany, it would look like this, nearly covering the whole country. Accordingly, there's a high interest in installing PV in desert areas. So knowing the high potential for PV application in deserts from irradiation point of view, we also need to point out that there are some additional stress factors compared to other climates in the world. You will have increased UV degradation, you will have dust and also high temperatures. In the spider diagram in the lower part of this slide, you can see some examples of different environmental parameters as given for deserts in red and for moderate climate in blue. And what you will find is that especially the irradiance dose will be increased, which is positive in most of the ways, but also it leads to increased temperatures of your PV modules. On the other hand, you have an average increased ambient temperature, and you will also have a soiling rate which is much higher, like up to 50 times depending on the location where you are. Wind speeds could be much higher in some deserts, and also the temperature change between day and night could be increased. And this environmental stress leads also to necessarily more O&M and less lifetime of the PV modules, which is because different degradation modes and performance issues, which will be shown on the next slide. So first, starting with durability issues, you can see some example degradation modes caused by UV on the left side, which is, for example, discoloration of the backsheets or delamination of the polymers. And on the other hand, you can also get a formation of hotspots because of breakage of taps between the solar cells. On the other hand, we don't only have durability issues, we also have performance issues, which are mainly due to high temperatures on the one hand, which you can see really on the right, and also due to soiling, the deposition of dust and dirt on the PV modules blocking the sunlight. The good thing about these things is that we could address them both by optimizing our PV modules, especially for the desert environments, and also optimizing our systems and our O&M to increase the yield and the service life of our plant. And with that, aiming at lower levelized costs of electricity. Now, and in the following, I will pick some of the specific issues and show some results and some ideas how we can address the challenges which we face in the desert environments. Here, starting with the example of high operating temperatures. So, generally, PV modules perform bad at high temperatures. So we have temperature coefficient, which, depending on the PV module technology, is in the range of 0.2 to 0.5% loss per increase in Kelvin. That means that at about if it's about 20 degrees warmer, you can have at least 10% less output performance for your PV system. A potential solution to that could be, for example, the adoption to half-cell design, as shown here. So here on the right side, you can see a solar cell which was cut in half, and due to that, we will get much less electrical losses in the interconnections, which is due to the fact that this depends on the square of the current, which then will be halved because we cut the cells in the center. And less electrical losses will also mean we have less heat dissipation in our PV module, which will end up in lower module temperature and at the end in a higher energy yield. And in addition, we could also get an extra energy gain from back reflection from the backsheet because we now have a gap between the cells. That this totally makes sense is also shown in the market currently, which moves strongly towards half-cell modules. We proposed it already back in 2016. And on the next slide, I want to show you some of the results which we had on half-cell modules. So here we fabricated the same materials, half-cell modules and full-cell modules, and put them on our rooftop at Fraunhofer CSP, and we looked at the temperature behavior, and we sorted, given in red, the full-size module, and given in black, the temperature of the half-cell modules. We had a temperature difference of more than 3 or up to 3 Kelvin, which is quite a lot and could give us like more than 1% of energy yield. Another thing I want to stress out or look at is the temperature difference problem, which causes some cell displacement. So between day and night, we typically have temperature difference up to 40 degrees in the desert environments, as you can also see from the environmental data, which is an example from Qatar in July 2015. And these temperature differences, which is effectively a thermal cycle, will cause a cell displacement in the laminate, as you can see in the example graph. Due to the cell displacement, there will be some extra fatigue on the tap because it moves all the time. And in that case, if the tap breaks, then you will have a reliability issue which could lead to hotspots or simply also in a reduction of your PV module output power. So, same as on the past slides, half-cell modules could be a solution to that, and here we want to present some results which we did on different tap interconnections, and for that we use different components and designs of PV modules, and in order to see the cell displacement within the module, we sprayed it with color to measure the displacement with an image correlation analysis. And here you can see some examples. We used EVA, we used also polyolefin as an alternative. We changed the spacing between the cells, and we also moved from full cell to half cell design, also changing the tap width, which could also improve our optical performance of the PV module. Then we used temperature cycling between -40 and +85 degrees. And on this slide, you can see the results of image correlation analysis. Seeing the original image on the left side with the area of interest, and then in the center you can see an image with a color code depicting this displacement. And the most interesting is the graph on the right hand side, indicating the gap change for different temperature ranges. And what you can see here is that there was no significant change in the when we changed the encapsulations from EVA to polyolefin, and also the changing the spacing had not a detrimental impact. But there was about 50% less cell displacement by shifting from full cell to half cell design, with barely any changes with the tap width again. So half cell modules could really reduce the issue of interconnector breakage, which is a nice result. Now I want to jump into the topic of UV degradation. As we have seen before, in the deserts we could have twice higher irradiation doses overall, which means also higher UV dose. But in addition to the irradiation, we also have a spectrum-dependent component, further increasing the UV dose by about 50%, which is because of the AM1 compared to AM1.5, which you have in the typical climates. And this will lead to discoloration and delamination, as we have also shown before. In order to see the impact of UV degradation on different materials, we did a benchmark test on 7 polymers, which were used for encapsulation and had different properties. From those, we prepared closed polymer glass samples and exposed them to UV of up to 270 kilowatt-hour per square meter at 60 degrees Celsius, according to the IEC 61215. And here you can see some results, some optical results. First, to see how the transmittance changes, and with the transmittance also directly connected, the PV output will change. And here we had some EVA with UV cut properties, which degraded by 2% after the 270 kilowatt hours per square meter. And this was, for example, not the case if we had a UV transparent EVA. In comparison, we also looked at polyolefin, and for those, the polyolefin with UV cut properties didn't show any significant changes, and the same was also for the UV transparent polyolefin. In conclusion, the UV cut polyolefin outperforms the EVA, and it can protect the backsheet, for example, as a rear side encapsulant, and the UV transparent foils are all equally good concerning the UV. In conclusion, one can say that it's really important that one checks the materials for their reliability according to the UV. And this can really change the output performance. Now, coming from temperature effects and UV degradation, I want to focus on another topic, which is one of the most detrimental problems in desert environments, which is the soiling of PV modules. And this is especially caused by airborne dust concentration, and in the deserts it's typically the mineral dust which settles on the PV modules and leads to power output reductions, as you can see from this very nice video here. But to put it more into numbers, here you can see the average annual airborne dust concentration, which is especially high in the so-called global dust belt, reaching from North Africa over the Arabian Peninsula to India and China. As a result of high airborne dust concentration, dirt accumulates at the glass surface, blocking the sunlight and significantly reducing the power output up to 70% or even more. In the photograph, you can see an example of a PV plant in India, which got heavily soiled and partly cleaned. In order to better understand the global impact of soiling on solar power generation, the graph on the left is showing the total installed PV capacity in gigawatts for major PV markets, including China, the United States, India, Germany, and the Middle East, for 2018 and expected values for 2023. On the right side, the corresponding soiling losses, as reported from literature, are given in percent loss per day. A soiling rate of 1% per day means that after 3 days without cleaning, you will have 3% total power output loss. There's a huge variation of soiling rates between, but also within the countries. However, one can state that by 2023, more than 500 gigawatts of PV will be installed in soiling-prone areas. From this data, and assuming the economically most optimum cleaning scenarios for the different regions, it follows that in 2018, soiling caused about 3 to 4% annual power loss globally, which is expected to increase to 4 to 7% by 2023 because of the high installation rates in the air polluted areas, such as the desert areas of the Middle East. This makes soiling a severe problem for our future energy generation. The most commonly approach to mitigate soiling is currently cleaning, so this is the state of the art. And there you can divide into different methods like manual cleaning, semi-automatic cleaning, or fully automatic cleaning. And actually there's no universal method recommended However, often wet cleaning is preferred, but it strongly depends on the local capital and labor costs for which methods the plant operators go. Concerning the fully automated cleaning, the market currently is very, very small, like 0.13% of the current global solar capacity, but it's also expected to grow to 6.1 gigawatts in 2022. On this slide, you can see the currently discussed or newly proposed soiling mitigation strategies, including anti-soiling coatings in A, B tracking, C electrodynamic screens, D dew mitigation, E module design, or F site adaptation. And in the following, I will give you some details on each of the methodologies. Let's start with the anti-soiling coatings, which are more or less the holy grail in the soiling research, depicting coatings which can reduce the soiling in a passive way. And there are different mechanisms which we found to be important, which could reduce soiling, including the effect of rebound, when particles bounce directly off the surface during impact, and also the effect of resuspension when wind blows off the particles from the surface. In addition, there have been also some studies on the interaction with dew and rain, and there we detected the processes of caking, which is kind of particle agglomeration at the surface, which could reduce the optical losses, as well as cementation, which fixes the particles at the surface and permanently glues them together with the glass. And last but not least, also the safe cleaning, for example, during rain. And so far we have seen significant reductions for all of these processes in the range of 20–30%, or even when it comes to reduce water condensation and reduce cementation up to 65%. However, these results were also very dependent on the local conditions. For example, we performed an outdoor benchmark test using different anti-soiling coatings and exposing them at 8 different locations in Saudi Arabia. And we exchanged samples on a monthly basis. On this slide, you can see some results of one of the best coatings. Here for 2 different locations. One is Al-Kafji, which is more coastal area, close to the Persian Gulf, and Solar Village, which is close to Riyadh in the central desert. And you can see that the anti-soiling coating, which is the red line, has less soiling in most of the months compared to the uncoated reference. And the relative benefits varied between 0 and up to 90%, depending on the months. And also in some months we had more soiling on our coatings, which could also happen. But anyhow, on the average, we had more than 30% soiling reduction, which was a really nice outcome. In order to design these coatings, we also used laboratory soiling experiments with a new test setup which we designed and which is also commercially available, together with standard for soiling testing, the VDI 3956. Another approach could be the change of tilt angles and the use of solar trackers. It is known from literature and many outdoor experiments that the steeper the tilt angles, the lower is the soiling rate. And also an important fraction of soiling deposition occurs during night. So we've seen that if one uses, for example, nighttime storing at 90 degree or 180 degree, one can decrease the soiling rate by more than 40%, which we have also seen in outdoor experiments. This mitigation strategy is also widely employed in concentrated solar power. However, the typical PV trackers which are there on the market have only angle ranges between 45 and 60 degrees. So it still needs to be checked how cost-effective one can adopt. Here I want to show some of the outdoor results, which we did on small glass samples, comparing different tracking algorithms, starting with a reference here called B. And when we put the glass samples to 90 degrees during the night and also to 180 degrees during the night, while they were tracking the sun during the day, we had an average soiling reduction of 41% for vertical and up to 50% for upside down. And this was also shown already in 2013 by First Solar, that even with the normal trackers, you can just use steep nighttime positions, strongly reducing the soiling with up to 30% already at 65 degrees storing. Another technique is the electrodynamic screen. So here we have the cleaning performed by a time-varying electric field at the surface of the PV module, which repels the dust particles. This technology was formerly developed for Mars robots by NASA, and it was also successfully tested in the laboratory and in controlled environments. However, we also have some limitations. It has some problems with harsh conditions and especially with high relative humidities, and currently the costs are very, very high. Nevertheless, I want to give you a kind of impression of such a system here. You can see how it looks like when there was dust on the surface and then it's turned on and the dust moves towards the surface edge and comes down. Further mitigation strategy could be surface heating. And since most of the soiling deposition occurs during the night and also is correlated to dew formation, which happens also mostly during night and early morning hours, soiling can be mitigated by preventing the dew formation. And for that, we can use different concepts like passive heating, for example, using phase change materials, also active heating, or using low emitting coatings. And to evaluate this, we conducted an outdoor study in Qatar for 4 weeks, using a set of samples with one glass coupon being heated by a heater pad and one unheated reference. After 4 weeks, we found a significantly reduced surface coverage for the heated coupons, which resulted in about 65% reduction of the optical losses. Looking at the samples by scanning electron microscopy, a significantly reduced amount of needles was detected for the heated sample. These needles are cementing materials in the region of Qatar, so by heating we strongly reduce the cementing effect. And accordingly, it could be proven that the needles form at the surface during dew events. Because of the high potential of the anti-soiling benefits, the prevention of dew and cementation was suggested by us as a possible new soiling mitigation strategy. In general, soiling can accumulate both homogeneously or inhomogeneously on the PV modules, for example at the bottom frame. The PV module orientations and design can reduce the impact from this inhomogeneous soiling, as will be shown in the following. The problem with this inhomogeneous soiling is the partial shading, which can degrade the power output significantly more than the same amount of dust spread uniformly. For example, shading only 50% of a single cell can trigger the bypass diode of a string. Accordingly, we can use frameless modules to avoid dust collection at the edges, but also different orientations and the design of half cells modules can be used. We did a kind of nice experiment with different PV module designs in order to show the different impact of inhomogeneous soiling, comparing the performance of full cell, half cell mirrored, and a half cell uniform design, while shading the lower row of the solar cells. So here in this example, you see how it looks like if we shade 50% of this lower row. And as you can see in portrait mounting, the half cell uniform design outperforms the full cell of 60 cells, which is completely gone if the bottom row is shaded. So In the case of portrait mounting and edge soiling, up to 65% higher energy generation is possible simply by changing or choosing the PV module design. Last but not least, also site selection and adaptation could be used as a soiling mitigation strategy. So soiling mitigation already starts with the plant site selection and the design. For example, the closer we are to a dust generation source, the larger is the soiling risk. And we could look for climate conditions which favor or limit soiling deposition. And there are different approaches which we can use. For example, we can design our system so that cleaning is easier, and we also reduce the number of dust sources by paving the roads, for example. And we can also install dust barriers or use chemical soil stabilizers. The solutions have to be tailored to the specific sites, and there's a lot of research to be done because so far I'm not aware of any study which looks really much into detail of that. In this slide, you can see again a summary of the discussed soiling mitigation strategies. In A, you can see the anti-soiling coatings, which reached up to 25% reduction in various experiments at feasible costs. However, the coating technology still needs to be adapted to the local conditions, and there's currently no one-fits-them-all solution. The option of trackers seems to be reasonable, as there is a very big trend towards one-axis tracking in PV in high insolation areas. And we could combine this with the adopted night storing positions in vertically or upside down. With a soiling reduction potential of up to 50%, as shown during some first experiments, for example in Qatar, we still not know if the costs are feasible for adopted tracker designs. In figure C, you can see again the electrodynamic screens, removing the dust with electric fields. And for the time being, this technology seems to be efficient in dry environments, but it's way too costly. Q mitigation was firstly proposed by our group, and we showed a reduction potential of up to 65%. However, the cost feasibility needs still to be proven. The effect of inhomogeneous soiling could be simply reduced by up to 65% by using different module designs which are already in the market. So there is no cost constraint here. And last but not least, the adoptions of the site. There we still need to do more research to see how this helps. Now I want to summarize my talk. I hope you've seen that PV application in desert environments could imply high gains due to the increased irradiation, but however, we also have some stress factors resulting from the environment, which could lead to reduced PV performance and also to reduced lifetime, which leads to higher costs. These are especially high temperatures, the effect of soiling, UV degradation, and also high temperature changes. However, there are many promising approaches concerning module technology and PV materials, as well as system design and O&M strategies. And with that, I want to thank you for your attention, and I'm open to questions.
So thank you, Clemens, for this nice talk. And now I'm waiting to see if there are any question from the audience. Still
I have
no?
one question, Hisham.
Okay, Professor Rashid.
Hi, Clemens, how are you? Thank you very much for your
fine.
contribution to the
Thank you.
To the conference. So it was very nice talk. I mean, we learned a lot. I have actually two questions. One is about this encapsulation material. You mentioned that PO is outperforming EVA in some cases. What is PO actually? Can you explain what it is?
It's polyolefin.
Polyolefin, yeah.
Which,
okay.
Yeah,
it was also TPO, right? TPO is also another name of that?
I think so, yes.
Yeah.
But
yeah, okay.
I am not an encapsulation expert. So
okay, good. Another question for the solution of this temperature degradation. I mean, in this area, I mean, in the hot climate, you have reduction of the efficiency due to the temperature degradation. Is it a floating PV can be a good solution to this problem? Do you think? In the Gulf states, for instance, in Doha or in those regions, installation the system on the sea, for instance, can be.
So, in general, I'm not aware of studies which looked at the temperature behavior of floating PV in desert environments. So I know that there are many studies, for example, from Japan or the Netherlands, which where the temperature is not that big of a problem. One thing one should really consider is that with you indeed will have also additional reliability issues because of the high humidity, but this is still an open research question. From my point of view, that could be a nice approach. Also, because then you have a lot of water for cleaning, for instance. But according to the temperature, I can't give you an adequate answer right now.
Okay. So thank you. So I have another question from Emre Demirzan. He's asking you, within your studies or researches, do you also consider or analyze the prevailing regional wind characteristic, direction, and speed of the world region where PV modules are affected by soiling?
Concerning the wind direction, we also looked into that, but I'm not aware of studies which are more or less not very site specific. So what we've seen is that besides the predominant wind direction, also the local conditions and especially the local conditions of turbulences in the PV plant, for example, could be much more of importance. For example, that the PV modules which are really in the front of the plant or which are close to some routes, ways through the PV plant, that they get much more soiled and more independent of the predominant wind directions. So if the predominant wind direction is in the direction of a dust source, this is really a problem. But if you're in the center desert, it sometimes doesn't even matter. Okay. From what I've seen so far.
Okay, thank you again. So I will move now to next speaker, Bushra El Arabi from Mohammed V University in Rabat. So she's a PhD student at Physics of Semiconductors and Solar Energy Research Structure, ENS, Mohammed V University of Rabat in Morocco, and she's also a research fellow at Vilhor Institute of Technology in India. So I suppose that she also has a pre-recorded presentation, so we can listen to her talk now. Okay.
Bushra El Arabi from Physics of Semiconductors and Solar Energy Research Structure in Mohammed V University of Rabat, and also research fellow at Vilhor Institute of Technology, Vilhor, India. And I'm going to present a review on modeling and prediction of soiling effect on on photovoltaics and solar and concentrated solar power module performance. So my presentation is divided into 3 sections. I'm going to start with an introduction, and secondly, the meta-analysis and discussion, and finally, conclusions and recommendations. So as you all know, soiling phenomenon is a serious problem which contributes to the decrease of solar irradiance received by the PV modules and lead to the decrease of the energy productivity of the PV or of the solar PV systems. So first of all, we notice that many reviews on soiling phenomenon have been published. However, although modeling of soiling effect is addressed in a significant a significant part of the studies published, no review of this part of literature has been performed yet. So this can be clearly seen in the summary of reviews in which we marked the aspect discussed in each review, and the only review that include modeling of soiling phenomenon is this, and it is only like not fully focus on modeling, like it includes other parts also. So as we work on modeling of soiling phenomenon, we got the idea to do this review and fill this hole, and the aim of this review is like we hope that this review will serve as a reference for future studies. So as we are talking about a review, then it is necessary to talk about the number of used references. As you can see in this form, the total references used is 141, and 59 is like have been used in the meta-analysis, 51 in the introduction, while 31 references have been used to explain more the applied models. So the used models or the used references include only journal articles, conference papers, and book chapters. And the research for relevant publication has been conducted based on the following keywords: solar energy, soil and modeling prediction in the following databases. So let us move now to the meta-analysis and discussion. The main part of the review is based on the summary presented in this table, where we summarize the different published papers. The summary includes the location of measurements, the used technology, the applied modular methodology, and comments. And in the comment parts, we precise the performance of the model, the main conclusions or recommendations resulted, not according to us, but according to the authors themselves. So from the body of the work performed, it has been concluded that many models have been used to study the soiling phenomenon. These latter have been applied on different technologies, as you can see here. And from this, it can be seen that the PV technology is ranked first with a percentage of 79%, followed by CSP technology with a percentage of 13%. And this, like this part, which is all technologies, it includes models that we expect their usefulness for all technologies as they concern the simulation of soiling potentials. So to be able to analyze the state of the art, the articles gathered and summarized have been divided into two groups. The first group is the theoretical modeling, and this category represents all models based on physics laws, and the statistical modeling, and this part or this category, it focuses on models based on statistical analysis of data. So the research papers gathered in this review show that approximately 68% of the studies conducted concerns the statistical modeling, while just 32% were about theoretical modeling, as you can see in this chart. And it shows also, on the one hand, that research regarding soiling phenomenon increases throughout the years. On the other hand, it confirms as well that the focus on statistical modeling increases in the last years against the theoretical one. So like this part, like the theoretical, this last part, which is like the theoretical modeling, shows a variety in terms of the applied models with a high use of solar radiation attenuation through the atmosphere laws. The analysis of this revealed that the construction of this type of modeling is based on some hypotheses that are in most cases far from reality. These hypotheses are, for example, the particles are spherical and have the same size, the particle distribution is uniform. The second layer of particles is deposited or formed just after the full formation of the first layer. And this explains the low percentage of use of this kind of modeling. So for the statistical analysis, the repartition of the applied model is presented in this graph. So from this, it can be seen that most of the model used were based on the regression analysis with a percentage of 44%, followed by neural network with a percentage of 23%. However, all comparisons conducted between neural network and regression analysis have shown that neural network were more accurate and reach better results. Nevertheless, neural network do not serve to understand the physical meaning behind the used data, which the regression analysis can do. Indeed, they are more accurate in prediction and useful to solve complex phenomena. So according to the recommendation of this reference, the modeling of soiling should be done in two parts. The first one should concern the model which will predict the amount of dust mass deposited according to the climatic conditions, while the second part should focus on the model which will correlate the amount of dust mass deposited and PV model losses due to soiling, of course. So based on this statement, we made the classification like the following classification, which includes all the process of soiling. So as you can see, there are three main elements: the weather conditions, deposited pollutants, and losses, and from which we extract 6 categories or 6 groups. So the first group is the group A, which is the modeling and prediction of soiling potentials or dust concentration. The group B is the modeling of the interaction between deposited particles and the surface. The group C, the determining the patterns of losses due to soiling. The group EB, which is the use of weather conditions to predict deposited pollutants. The group BC, which is the correlation between deposited pollutants and losses due to soiling. And the group EC, which is the correlation between weather conditions and losses due to soiling. So for each group, we presented the number of publications. So based on this figure, it can be seen that the highest value belongs to the group BC, followed by the group EC, then the group C, and at the end we have like the group E and the group EB. So for the two models suggested by the previous reference are the group AB and BC, and these two groups are complementary to each other. So for the part B, which is about the deposited pollutants, there are many published papers which describe and model the interaction between particles and the surface. This part is also an important one, but it is far beyond the scope of the present review. So from the summary of reviews we mentioned previously in the introduction, the factors that affect soiling phenomenon can be categorized and summarized as follows. So we have here the model characteristics, the climatic conditions, surrounding environment, exposure conditions, and soiling properties. So based on this summary and based on the previous classification, from which we selected the paper that use the factors that influence soiling to model and predict deposited pollutant or soiling losses, we determined the factors that have been used widely to predict soiling and those that were rarely taken into consideration and present them in this figure. So from this, we can clearly see that the factors that mostly used are the ones belong to the category of climatic conditions, especially temperature, relative humidity, rainfall, wind speed, and airborne dust. This can be explained by the fact that with almost every solar installation and weather station will be available, which make it easy to consider the weather conditions. For exposure conditions, module characteristic and the surrounding environment are mostly fixed for every module in a specific study due to the difficulty to obtain data for all conditions. Not taking into consideration all factors represents the lack in almost all models, and in many papers, this has been considered as one of the causes to obtain low performance of their models. So to sum up, the review shows a variety of the applied models and methods. Each model has its own strengths and weaknesses. However, in order to approach the complex behavior of soiling phenomenon and to predict it over time accurately, more data for long periods are still needed. Moreover, all parameters affecting soiling should be taken into consideration. And furthermore, as it has been previously proved that dust concentration ranks first in predicting soiling losses, the use of existing databases of soiling potentials adjust using weather conditions from existing databases or from meteorological stations seems to be a low cost and valuable method to predict soiling losses. And finally, instead of suggesting new models, it will be wiser to test published models that have proved good results in different sites and on different technologies to overcome their limits and to achieve the accurate and well-tested model. So this review will help researchers working on this topic to gain an overview of the models used or applied. It will also help to better choose the right direction in modeling and predicting soiling phenomena. Understanding and mastering this phenomenon will not only prevent investments from losses, but also save the precious natural resource water by determining the mitigation techniques wisely. At the end of this presentation, I would like to thank all the co-authors of this work for their valuable contributions. I also seize the opportunity to thank all organizing and scientific committee of this successful conference. Dear audience, thank you for your attention.
So thank you, Bushra, for your nice review. So I think we have time to take short question from the audience. So which different climate, different than Morocco, you are planning to test, to test your model on now? So
hello.
Hello.
Thank you for your question. Actually, I am I was doing an internship in India, so I have already recorded data from there. So that is my Indian climate.
So did you have results so far from Indian climate and how you compare it with your climate in Morocco?
Yes, we didn't do yet the comparison, but we did the study there.
Okay, I see. So thank you again. Now we come to the last contribution in this workshop by Abdul Latif Bouaishe, who recently received his PhD, and he works as a researcher in Irizin in Morocco, where he does research in PV performance in harsh conditions of Morocco. And I suppose that his presentation is pre-recorded, so we can listen to that now.
Hello everyone, thank you for being here today. I'm Abdul Latif Bouaishe from Morocco. I'm going today to talk to you about our work toward the development of a desert PV module in the Moroccan climate. As you know, during the real outdoor exposure, PV modules are influenced by various climatic stress like mechanical stress, thermomechanical stress, partial shading, UV light, temperature cycle, and so on. Whereas during the qualification test, these stresses are not necessarily applied together, which must result in the generation of the same type of defect, particularly in desert region with harsh climatic conditions like Morocco. This is why it's important to test the durability of modules in real conditions in order to adapt and optimize new conception of PV module for the market of tomorrow, which are the MENA region and Africa in particular. In this context, the Research Institute for Solar Energy and New Energies, RISEN, in Morocco, has established a new research platform called the Green Energy Park at Bengrir, Morocco, to test and monitor the degradation of different PV technologies over time, depending on the specific climatic condition of the city. So, the Green Energy Park is consisting of various technology like crystalline technology, CIGS, CES, CDTE, micromorph, concentrated solar power for different manufacturing. The objective is to compare the different technology in order to select the most adapted to the context of Morocco. As the methodology of our work, in the present study, the PV module durability was carried out according to the approach illustrated in 3 steps. The first one is the deployment of a number of PV modules in outdoor conditions for long period for more than 3 years for the inspection of the failure mechanism specific to the harsh climatic condition of Morocco. The second step is the proposition of new materials and process and design to each defect. And this third one is the validation of the proposed solutions by accelerating edging tests and also by outdoor exposure. In the present study, we focused on the crystalline technology by selecting 5 PV systems from 5 different manufacturers. So, for each system, we select a PV string as a sample. For the inspection of the module gradation mechanism in the Green Energy Park platform, we restored to advanced techniques like electroluminescence, like infrared imaging, like the measurement of the electrical parameter, in addition to the visual inspection. So, as a result, after the inspection of the selected PV module, various degradation modes relating to the climate of Morocco have been observed and detected. These degradations are manifested as hotspots, as delamination, snow trails, PID, cracks, microcracks, and discoloration. In parallel, the electrical parameters were measured and compared with the one provided by the manufacturers, and in this study, the measurement of individual module was performed in real condition with the EV tracer. For a high accuracy of the EV curve measurement, the measurements were taken around none and at clear sky condition with irradiance intensity between 800 and 1100 watts per square meter. Also, before any measurement, the selected PV module were cleaned to eliminate the effect of soiling. For the results of the power degradation of the 5 inspected PV systems in Morocco, these figures show the individual power degradation rate for the PV module of each selected string, as well as the average degradation rate. As clearly seen, for the 5 systems, all the PV systems show high degradation rates. So this result is not favorably compared with that given by the manufacturer with 0.8% per year as an average degradation rate for crystalline technology. In fact, the power drop in the present study is mainly related to the harsh climatic condition of the studied operating set. In addition, the high degradation rate reflects the relatively low expected lifetime for the module, as the manufacturer gave about 25 years as as lifetime PV module with a maximum of 20% of power drop. This found degradation rate for the present study are very high. So this may influence dramatically the project's development of PV module plant, especially in the plant's economical calculation and payback time. So it's recommended in the present study to develop a new PV module generation called like a desert module dedicated to harsh desert climate. So this is by mitigation of the real observed degradation in Morocco and the different observed degradation mode in the green energy park. So our next step will be the proposition of some solution for a desert PV module based on the observed degradation mode in Ben Guerir, Morocco. So, in order to further quantify the results of the analysis of the Moroccan degradation modes, we consider a classification based on the severity of the different observed degradation modes. So, these two tables, the first one presents the various defect function of the inspected system in Morocco, and the second one presents the observed defect with their severity ranking as reported by Jordan et al. Accordingly, the Pareto chart for the defects reported in this study is plotted. And as clearly seen, the potential degradation modes in this survey are hotspots, cracks, and PI. So, in what follow, mitigation solutions against the three modes dominant in the climate of Morocco are recommended. Let's start by the first one, which is the cracks. So, during the operation of PV module, temperature cycle, mechanical stress, and thermomechanical stress are the main causes behind cracks and microcracks in PV module. As the solutions, we proposed some solutions in the cell level, in the module level, and in system level. In the cell level, we propose to use half cell against full cells in order to reduce the problem of cracks. In parallel, we can reduce the cell temperature by using the PERC technology and also to improve the efficiency of the PV module. In the module level, using the encapsulation material should be less stiffness to improve the mechanical protection of the PV module. And the system level, we recommend to use 6 fixing points against 4 fixing points in the PV module in order to reduce the bending of the PV module after the effect of wind load. So, for the hotspot, this problem results from internal problems like cracks in PV module, inhomogeneous dust deposition, or heating of the bypass diode inside the junction box. So, the mitigation solution for the hotspot is necessary, and it is necessary to take into consideration the listed cost. For the first one, it's necessary to reduce the cell defect by preventing cracks and PID. So we talked about cracks. Also, it's necessary to prevent the partial shading in the PV module, which is very pronounced in the climatic condition of Morocco and especially in Ben Guerir, by cleaning or by using an anti-souling to improve, and also using a coating to improve the durability and to gain high power output against souling effect. For the heating of the bypass diode inside the junction box, so several manufacturers have introduced a new class of active bypass diodes. This technology uses transistor to produce similar behavior of the diodes. With this technology, The junction box can be simplified or eliminated, and the number of diodes can be increased, which can improve the performance in the partial shading condition. So, for the PID, the encapsulating layer of the cell must provide the perfect electrical insulation in order to mitigate this problem. As you know, in the PV market, the FVA remains the most dominant due to their low cost. So there is certain polymers which can be considered and as alternative. So there is, for example, the PVB, the TPU, the silicon layer, the polyethylene, the ionomer. So the encapsulant with low water vapor transmission rate and high resistivity is the most important solutions. So in the present study, the polyethylene and ionomer have similar resistivity value, have a high resistivity value, but polyethylene has other interesting processing properties since it requires no change at the machine. So in the present study, the polyethylene could be good and reliable solution for encapsulating material thanks to its low cost and high resistivity. Finally, after the inspection of 5 PV systems in the climate of Morocco, we found that the measured degradation rates are higher than that given by the manufacturer, which is 0.8% per year, which is due to the harsh climatic condition of Morocco. The observed degradation modes are cracks, hotspot, delamination, encapsulation, discoloration, snail trails, and PI. For this, we recommended to develop a new PV module by mitigation of this real degradation mode in the climate of Morocco, and there is some solution which have been proposed. The next step is the validation of the proposed solution by accelerating agent tests and by outdoor condition of Morocco. In Morocco. Thank you for your attention.
So thank you, Abdul Latif, for really this nice, the nice and exciting presentation. We are already behind the schedule, so I will take only one very short question. So you tested crystalline silicon system, and the question is, what type of crystal silicon technology are these module based on?
Okay, thank you for your interesting question. So in our study, we tested crystalline silicon because which is the most dominant in the market, and we have demonstrated in our previous study that crystalline silicon is the most suitable for Moroccan climate. So for your question, we tested the monocrystalline and polycrystalline silicon technology.
So it is it PERC or, for example, PERC or heterojunction, or there are different types of crystal.
The tested module are the standard module in the market, aluminum box surface film.
Okay, I see. Because as far as I know, silicon heterojunction are known to be more resistive to hot climate.
Yes, of course. There is
Okay.
also some PV module which are exposed here in Green Energy Park with different manufacturer and different technology like PERC, but the tested module which must be exposed for more than 3 years doesn't not like heterojunction or PERC technology.
So I wish you success and congratulations again for your PhD that you received last week, probably. Okay. So now I'm closing the workshop on EXtremePV. And I would like to thank our keynote speakers and presenters for sharing their results with us. And in 10 or 5 minutes, we will have another session on PV performance and reliability. with again some nice and exciting topics. So I'm closing this session and thank all the speakers and the audience for being here with us. So see you hopefully next Pvcon with probably another EXtremePV workshop. Okay.
Thank you very much.
Bye
Thank
bye.
you very much.
Bye.